Hey, folks. So, another of the weird things that you can figure out, that you can study when you're studying galaxies, is that some galaxies are quote-unquote active, and some aren't. And what makes a galaxy active is that a lot of its brightness, a lot of its luminosity, is coming from something other than stars. If you're looking at the spectrum of a galaxy, the same way that you can look at the spectrum of a star, take the light from a galaxy, shine it through a prism, break the light up into the spectrum, and see what the spectrum looks like. And a normal, not active galaxy, the spectrum tends to look something like this, where you're seeing the light from mostly stars, right? Bright in the visible, bright in the infrared, and the flux, the luminosity tails away, just like any black body does, just like any continuous spectrum will show you. There's absorption lines, of course. There's absorption lines in a galaxy spectrum. Why? Because there's absorption lines in the star's spectra. But it looks, roughly like this. An active galaxy is giving off all kinds of light, extra light at all wavelengths, especially the radio and the X-rays. And so you look at that and go, what's going on there? There's something else giving off light that's not just normal old stars. And, when this was first being studied in the 1950s, people started looking around for these active galaxies, and some of them look kind of like this, and some of them look like this, and a lot of them look different for different reasons. And you go, what a lot of astronomers thought was, how can there be so many different kinds of active galaxies? Are they all active for the same reason, or are they active for different reasons? And one of the big discoveries of the 21st century, one of the big discoveries about galaxies in the 21st century so far, is that it turns out they're all kind of the same thing. That the reason why active galaxies look different has a lot to do with what angle you're looking at them. If your eye is right there and you're looking at this galaxy, then it looks like there's a bright thing at the center, and that bright thing is shooting out jets. So if you're looking at this galaxy from this angle, you're going to see something like a radio galaxy where there's a bright object at the center and it's shooting out these jets north and south. There's a disk of dust and gas and stars in the foreground. So the dust here is kind of covering up what's going on in the middle. Unless you look at it in the radio, because radio waves have an easy time getting through the dust, and you can see that there's like one bright spot of an object at the very center. That there's some engine, there's some energy source, bright and compact, at the center of the galaxy, and it's shooting out these two jets. And that is basically the explanation for radio galaxies. On the other hand, if you're over here and you're looking at this galaxy, then you're getting the flashlight in the face, right? This jet is getting shot out in our direction, and then what do we see? Well, this disk of dust and gas and stars, well, we're looking at it from the bird's eye view, right? We're getting the side view here, and we're getting the bird's eye view of this disk here, and the bright thing at the center, what is that? That's the jet shooting right towards us. We're really getting the flashlight in the face. So there are more types than this, right? There are more types of these active galaxies. They look a little different in your telescopes, right? Quasars, Seyfert galaxies, radio galaxies. There's a whole zoo of these active galaxies that look a little different. But it turns out they're basically the same thing. The same thing is causing them to be active, just from slightly different perspectives from our point of view. Quasars look like stars. They're little dots, little spots in the sky, and then you think, oh, that looks like a star, let me look at the spectrum. And a star gives you what? Well, a star gives you what kind of spectrum? It gives you an absorption spectrum. And that's not what you get from quasars. When you look at a quasar, you get bright emission lines, especially from hydrogen, because hydrogen's the most abundant element, right? But you get these bright emission lines, not absorption lines, emission lines. And that's a telltale sign that there's something else going on there, right? This is not a bright star. It looks like a star because it's compact and bright and hot and shining, but we're not looking at a star because stars don't give you emission lines. So what are we looking at? It turns out, like I said, all of these active galaxies are powered by the same thing, and that is a supermassive black hole. Right? These active galaxies all have a supermassive black hole at the center of the galaxy. So what makes it active? Right? It can't be the black hole, right? The light that we're getting, the bright light, that's not the black hole, because light doesn't escape from the black hole. So what makes this galaxy active? What makes it so bright? And the answer is because this black hole is actively feeding, right? Gas is falling in toward the black hole, and it's falling into orbit around the black hole. And this gas is getting sucked in, falling into orbit of the black hole more and more, and the gas slowly spirals inward. And as the gas circles the drain, as the gas is slowly sinking in toward the black hole, the gas is going to get more compressed by gravity, right? As it gets closer and closer to the black hole, the gravity is getting stronger and stronger. The gas is getting more and more compressed until the gas gets so hot and dense that it glows, that it gives off light. That is the light from the active region, right? The thing that makes this an active galaxy is that it is actively sucking in gas until that gas heats up and glows. That's why the emission lines, right? This is a hot gas. It's a hot gas. What kind of light does a hot gas give off? It gives off an emission spectrum. So what's this gas mostly made out of? Hydrogen. So when there's hydrogen falling into the black hole, it gets heated up, it glows with its emission lines, and so you see the emission lines in the spectrum of the quasar. Right? We're not seeing light from the black hole, because light can't get out of a black hole. We're seeing the light from the accretion disk right outside the black hole. And how fast the black hole is feeding can change, right? Sometimes the black hole doesn't pull in that much gas. And if there isn't that much gas in the accretion disk, then it's not going to be as bright. And then the brightness will go down, right? Here's a graph of brightness versus time for an active galaxy, for a quasar. And, sometimes there's more gas, sometimes there's less gas, and the disk will get dimmer. But then you could have a big hump of gas that all falls into the black hole all at once, and right before that gas falls into the black hole, you're going to have a lot more gas. It's going to get compressed and heated by the gravity, and it's going to get really bright, and you're going to have a bright flare. And so it's going to get really bright. And then once all that gas falls into the event horizon, then there's no more light for it to give off, and then the brightness goes down again. And there's that cool trick. This cool trick is that how long this flare takes to happen, how long it takes to flare up and then fade away, tells you the size of the disk. It tells you the size of the black hole. Because if we're over here, if your eye is over here, all of this gas falls into the black hole at the same time. And so the light given off this way and the light given off this way, it's all leaving the disk at the same time, but the gravity near a black hole is so intense that this light can get bent around the black hole and shine at the Earth. Right? The light from the near side of the black hole has a head start, and it'll reach us first. It'll reach us here on Earth first. But the light that's emitted by the far side of the black hole, that light takes longer because it's bending around the black hole, and it'll reach us here on Earth later. So this light and this light left the black hole, or left the disk at the same time, but this light has a shorter path to take, so it reaches us first. This light has to go around the black hole and then head to Earth, and it's going to reach us later because it has to take a longer path. The difference between when the first light arrives and when the last light arrives, that tells us how much longer of a path this light had to take to get around the black hole, and that tells us the size of the black hole. We know the size of the black hole by the extra length that this light had to go around to start heading toward Earth. So, what are the characteristics of a radio galaxy? Are they bright or are they dim? Oh boy, they're bright. Right? You've got, the active galaxies are giving you luminosity from all the stars, and then the extra luminosity from the accretion disk. Is the light visible? Nah, it's all kinds of light. Right? What's the size of the emitting region? Well, you've got a black hole, which is very small, and then you've got this disk right around the black hole. So that's a pretty small region, right? That extra light is coming from this really small disk as it's about to fall into the black hole. Are there flares and jets? Oh yeah, right? The flares from when there's a whole bunch of gas that falls in. Where are the jets coming from? Well, let me draw a new cartoon over here. So we've got the black hole, we've got the disk with the gas falling in. As this gas gets heated and compressed by gravity, the gas heats up. The black hole could also have a magnetic field. Right? There could be a magnetic field around the black hole, and magnetic fields can exert forces on charged particles. And so as this gas is spiraling in through the accretion disk, it's being compressed, it's being heated, it's being ionized, right? The gas becomes a gas of charged particles, protons and electrons, that kind of thing. And so when this gas gets hot enough to ionize, once it becomes a plasma, then this hot gas can get grabbed by the magnetic field, and it'll get wrapped around the magnetic field lines, and that gas will get shot out as a jet. And this gas can get wrapped around this magnetic field, and then get shot out as a jet. So that's why these active galaxies have two jets, right? A jet of gas that got pushed out by the North Pole, and a jet of gas that got pushed out by the South Pole of the black hole's magnetic field. So, just like how you can have this flare when there's a whole bunch of gas that all of a sudden falls into the black hole, and the disk gets brighter and hotter and then flares up. Well, when there's a whole bunch of extra gas falling into the disk, then you can also have extra gas to get ionized, to get grabbed by the magnetic field, and then get shot out. So the flares and the jets happen at about the same time, over and over. Every time there's an extra blob of gas that falls in toward the black hole. So, what kind of conclusions can we draw about this? Well, here is the light curve for this. There's the name of the quasar. There's the serial number for the quasar. And if you watch it, it's usually like this brightness. The brightness of the black hole is usually, or the brightness of the disk, the brightness of the galaxy is usually like here. And then every once in a while, it'll flare up and then fade away. How much time did that take? Well, it looks like the flare started on, let's say, day 5. It flared up. It faded away. It faded away on day 8, let's say. Right? So the flare happened between day 5 and day 8. The first light from the near side of the flare arrived on day 5. The last light from the far side of the flare arrived on day 8. So how many days did that take? It took 3 days. It took 3 days for that last light to reach us. 3 extra days. So then the size of the emitting region must be 3 light days, right? That light is traveling at the speed of light. If it traveled for 3 days, then it traveled a distance of 3 light days. How many kilometers is that? Well, 1 light day is 2.59 times 10 to the 10 kilometers. So we can do that math. All right, we got 3 light days times, if we do 3 light days, times this many kilometers per light day, that'll give us the total number of kilometers. So we just need 3 times 2.59 times 10 to the 10 kilometers. Where's my spreadsheet? There you are. All right, we can do that. All right, so equals 3 light days times 2.59 E10, right? 2.59 times 10 to the 10 kilometers. That, that's a big number, but of course it is. It's a lot. That's a big length. So I'm going to turn that into scientific notation to make my life easier. Okay, 7.77 times 10 to the 10. All right, so the size of the disk, the size of the accretion disk around the black hole is 7.77 times 10 to the 10 kilometers. How big is that? Well, let's convert that into AU to make our lives a little easier. How many astronomical units is that? So we got the number of kilometers. If we take the number of kilometers, divide by the number of kilometers in an AU, that'll convert into AU. So 1 AU is 1.50 times 10 to the 8 kilometers. So I'm going to take that number, take the number of kilometers, divide by the number of kilometers in 1 AU, and that is 5.18 times 10 to the 2 astronomical units. What is that as a normal number? 518. That's easier to write down. So, the size of this emitting region is 518 AU. Well, the diameter of our solar system is, about 200 AU. So, if our solar system is something like 200 AU across, and this is 500, this is only a few times the size of our solar system. It's a few times the size of our solar system, but it's got the brightness of a galaxy. Right? It's so bright that it's adding all this extra light. All this extra light in the radio, in the visible, in the X-rays. All that luminosity, but packed into something, about the same size as our solar system. What could be that bright? What could be that powerful? What could be that powerful that you're giving off the luminosity of a galaxy, but in something so small as the size of a solar system? That's why we think it's a supermassive black hole, right? You can't see the supermassive black hole. All we're seeing is the light from the disk. And yet, what could be that powerful? What kind of phenomenon in nature could be so powerful that it's able to collect all that gas, heat up the disk, make the disk flare up this much for 3 whole days? That's why we think the best explanation for all of these active galaxies is that it's a supermassive black hole. I'll let you write that whole thing out, but, we abbreviate it to SMPH. It's a good explanation, right? You can't get a direct observation of the black hole, but nothing else that anybody's ever thought of is a better explanation for what is actively gobbling up all of that gas from the disk in the galaxy, in the core of the galaxy. One more thing, right? There's a black hole at the center of our galaxy, right? So why do we have a normal galaxy, quote unquote? why do we live in a non-active galaxy? We have a supermassive black hole, but our galaxy isn't like this. Our galaxy's like the Milky Way. And the answer is that you need more than just a supermassive black hole, right? You need a supermassive black hole gathering an accretion disk, feeding on an accretion disk. An accretion disk of what? An accretion disk of gas. Right? That's the difference between these active galaxies and our galaxy. Our galaxy has a supermassive black hole in the center, but it's not actively feeding. There isn't, our galaxy, our supermassive black hole in the Milky Way, occasionally some gas will fall in. Every once in a while, astronomers will sort of see a blob of gas make a gradual little, you'll see a blob of gas make a little spiral, and then eventually it'll disappear into the black hole. And it heats up and glows right before it falls in, but it's not a steady stream. Our gas it's feeding a little bit every few years, but it's not actively gobbling up gas out of the disk at a steady rate the way these active galactic nuclei are. That's another word. That's another word for the supermassive black hole. If the supermassive black hole is actively feeding, it's called an active galactic nucleus, right? It's actively feeding at the nucleus of a galaxy, hence the name. It sure looks like, from everything we see, that there's a supermassive black hole at the center of most galaxies, and yet they're not all actively feeding. Only the ones where there's a lot of gas falling through the accretion disk into the black hole and giving off light before it disappears, that's what makes the active galaxy active. Okay, I'm probably repeating myself from the lecture at this point. So, all right. There's similar questions here. There's similar questions here to what's in the practice. So go ahead and knock out that practice. Hopefully this math is making some sense. And onward and upward. All right. See you there, everybody.